You ever stop and think about the invisible magic that's powering, well, the very device you're watching this on right now? Today, we're going to unplug that mystery and take a look at what electricity really is.
Okay, think about this. It's something you do every single day, probably without even thinking about it. You flip a switch and bam, the light comes on. Instantly. But why instantly? I mean, how does that actually work?
So the first thing that probably pops into your head is that a little electron just zips from the switch all the way to the light bulb at like the speed of light, right? Well, that's what most of us think, but it's totally wrong. The reality is, individual electrons are actually super lazy. They just kind of shuffle along in what's called drift speed. We're talking a crawl, not a sprint, not even close. So if the electrons are so slow, what's the deal? Well, here's the secret sauce. When you flip that switch, you're not sending one electron on a marathon run. No. What you're doing is sending a signal, an electric field, and that signal blasts through the wire at nearly the speed of light. It's basically an instant command that tells all the electrons in the wire to start moving at the exact same time. It's like a chain reaction, like tipping over the first domino in a line that stretches for miles.
All right, so here's the game plan. We're going to follow the flow. First, we'll look at this invisible river of charge. Then, we'll talk about what gets in its way. After that, the simple rules for wiring things up, and finally, we'll see how we harness all that power.
Okay, first up, the invisible river. Let's really get a handle on what's going on inside that wire. We've got to define this flow of charge, what we call electric current.
So the best way to wrap your head around electric current is to think of a river, right? You're not trying to track the speed of one single water molecule. That'd be crazy. Instead, you'd stand on the bank and measure how much water, say how many gallons, flow past you every second. Electric current is exactly the same idea. It's just the total amount of charge that's passing a specific point in the wire every single second.
And here's where things get a little weird, thanks to history. See, we know for a fact that it's the negatively charged electrons that are actually moving through the wire. But way back when scientists were first figuring this stuff out, they took a guess. They guessed it was a flow of positive charge. And, well, they were wrong, but the idea stuck. So even today, by convention, we draw the current as flowing in the opposite direction of where the electrons are really going. Kinda crazy, right?
And check this out. Here is the number that just blows this whole thing wide open. That drift speed we talked about, it's about 10 to the minus 4 meters per second. We're talking a snail's pace. Slower even. It is unbelievably slow. And this just proves that whole paradox from the start, right? The instant light has nothing to do with how fast one electron moves, and everything to do with how fast that push signal travels to get them all moving at once.
Okay, so we've got this river of electrons flowing, but, it's not like a perfectly smooth, clear channel. As these electrons are trying to move, they're constantly bumping and crashing into things inside the wire. And all that bumping creates an obstacle to the flow. That obstacle is what we call resistance.
The easiest way to think about resistance is just electrical friction. That's really all it is. As the electrons are shuffling through the wire, they're colliding with the atoms of the material itself, and every single one of those collisions slows them down a bit and turns some of that electrical energy into heat. That's literally why your phone charger or your laptop brick gets warm when you're using it. That's resistance at work.
So what determines how much resistance a wire has? Well, it really boils down to three main things. First, what's it made of? Some materials are just naturally harder for electrons to get through. Second, how long is it? I mean, a longer wire is just a longer obstacle course, right? And third, how thick is it? A thicker wire is like a bigger, wider pipe. It gives the electrons way more room to flow, and that means less resistance.
And all of this, it brings us to maybe the most important, the most fundamental rule in all of basic electronics, Ohm's law. It's this beautifully simple formula that ties everything together. It connects voltage, that's the push, with current, the flow, and resistance, the opposition. And what makes it so powerful is that it makes electricity predictable. We can stop guessing and actually start designing and controlling electrical circuits with amazing precision, all thanks to this one little rule.
Okay, so a lot of the time in electronics, we actually want to add resistance to a circuit on purpose, and we do that with a little component called a resistor. But here's the thing. If you pick one up and look at it, you're not going to see a number written on it. It just has these little colored stripes. So how in the world are you supposed to know its value?
Well, the answer is this really clever color code system. It's basically a secret decoder ring for electronics. Every color stands for a number, and where that colored stripe is on the resistor tells you what its job is. It's a whole secret language.
And once you know the code, it's actually super simple. It's just a 4-step process. The first color band is the first digit. The second band is the second digit.
The third band tells you how many zeros to tack on the end, and that last band, that just tells you how accurate the resistor is, what they call its tolerance.
All right, so now we get how current and resistance work. We can actually start building stuff. And that brings us to the two basic fundamental ways you can wire things up to make a circuit.
First step, we have what's called a series circuit. This is super straightforward. You just wire everything up end to end, like cars in a train. There's only one single path for the current to take, so every last electron has to go through every single component, one right after the other.
The other way to do it is with a parallel circuit. Now, in this case, the path actually splits into multiple branches, so the current has options. It has more than one way to go. It splits up, flows through all the different branches at the same time, and then it all joins back together on the other side. And how these two setups behave? Well, it's night and day. In a series circuit, it's pretty simple. The more things you add, the more resistance you get. Easy. But parallel, this is where it gets really interesting. The voltage across every branch is exactly the same, but the current splits up. And here's the part that messes with your brain a little. The more paths you add, the easier it becomes for the total current to flow. So get this, adding more resistors in parallel actually lowers the total resistance of the whole circuit. I know, it sounds backwards, but it's true.
So why does any of this matter? What's the point of all this current and resistance and circuits? Well, it all comes down to one word: power. Power is the whole reason we do this. It's the measure of how fast electrical energy is being used to do something useful. You know, like lighting up your room or powering up your computer.
So power is simply the current multiplied by the voltage. That's it. It's the amount of energy being delivered by the circuit every single second. We measure it in watts, and that is ultimately what you're paying for on your electricity bill every month.
But here's another twist. None of these properties are set in stone. Take temperature, for example. It has a huge impact on resistance. For most normal metals, like the copper in wires, the hotter they get, the more resistance they have. But then you have other materials, like semiconductors, where the exact opposite happens. They get hotter, and their resistance actually goes down.
This whole relationship between temperature and resistance, it leads to a really fascinating question. If resistance in metals goes down as they get colder, well, what would happen if we could make them really, really cold? Like unbelievably cold?
And that question brings us to the absolutely incredible world of superconductors. See, if you cool certain materials down to extremely low temperatures, something amazing happens. Their electrical resistance just vanishes. It drops all the way to zero. That means you could get a current flowing in a loop of this stuff and it would literally flow forever without losing any energy. And this isn't science fiction, it's real. And the possibilities? I mean, we're talking about power grids with zero energy loss, levitating high-speed trains. It's the kind of thing that could completely change everything about our world.